terminals indoors. I have some collaborators, mainly from University of Toronto and some from Canadian National Institute for Blind. Let me just first show you, if I can get this. Yeah. Let's start with the video.
You are standing in the main corridor facing north on the second floor of CNIB. Room 207 is on your right. Please follow voice instructions to reach. Storage room, please. Walk straight for 25 meters and find the way on your left.
So as you can see, this is a navigator system working indoors, and it's meant to guide blind people to be able to navigate inside buildings. While you're walking, you can see that information about the environment is being delivered as speech prompts. For instance, here at this point, you are close to the elevator.
Go straight.
Let's see if it finds the elevator.
Elevator is on your right.
We were approached a couple of years ago to do this kind of research and to test it in practice.
Women's washroom is on your right.
So as you can see, all announcements are coming. So I'm going to cut the video in the interest of time.
Stairs is on your left.
Okay. So our objective is this. We want to design a system that can be deployed on commercially available mobile devices without any hardware enhancement to the system. So we are going to do localization, and we use the traditional format that people are using by doing some site surveys and then doing localization. Our localization has two parts, two components. One is coarse localization, and another one is fine localization. So our motivation for this, as I said, is to work to build a system that can be used with visually challenged people. And why is it important? Because just in Canada, it's about 2 million people are suffering from blindness or something called AMD, age-related macular degeneration. That with the baby boomers becoming old, we're going to see more of this. Now, if you look into these applications, ranging from E91 regulations to shopping mall advertisement to blind, you see that the precision is changing. Here, we're talking about sub 10 meters, maybe 1 or 2 meters. Basically, blind people, they can navigate or can find the objects using their white cane, but it's just about 2 meters or 1.5 meters about them. So this is the most challenging place. So what we want to do is we want to find our location. So the question is, where am I in this building? And I'm reading some signals that are coming from the environment. So we do the conventional way of fingerprinting. You collect fingerprint, store at some database, and then measure and compare to that. Now, what about the privacy? Given the fact that these blind people, they don't really want to be located by someone else. They want to locate themselves, but they don't want to be located by someone else. So you have to be careful here, because these fingerprints or this database, it's sitting somewhere in a server. Now we want to retrieve that database and use it locally to be able to measure it. So if you look into the perspective of the system design, is like this, that you're measuring the power coming from some access points here in the left-hand side, and then you write it into database. You measure your signal, and then you compare the two using some algorithm. Okay, and you find your location. So as I said, it is done in two steps. One is collecting fingerprints and putting it in a database. The user just fetches those fingerprints and does everything locally. It is done, all location estimation is done at the device. So from that perspective, you are controlling, or you're finding your location. It's not been done elsewhere. Okay? So it's not that someone else is locating you. So privacy somewhat observed. I don't want to go to the details here, but what we are using, which makes it slightly different from the traditional ways, is new advancements in signal processing called compressive sensing. Okay? So let's leave the theory aside. Our localization has two steps. One is offline and online. In offline, what we do is that once we measure the data using some mobile device, we put in a server. This server does this. It categorizes this data into different clusters. As you can see, with different colors, we're showing that. So this is called clustering. There are different methods that they exist for clustering. We use one of those methods. This is important for estimation, as I will show through some results. One of the major utilities of this, or usefulness of this clustering, is that it's removing the outliers. Okay? And this is the place that you want to gain a lot in accuracy. In the online phase, what you're doing is again broken into two steps. This is your user and this is the server. You make the measurement of the environment. You do something called coarse localization. You roughly know where you are. Then you communicate with the server and you say where you are if you want. And then information comes about your locality, and then you start with the fine localization. And this is the place that we get to sub 10 meters accuracy. So in coarse localization, basically what you're doing is you're finding your clusters, to which clusters I belong. For instance, in this environment, you might have 4 or 5 clusters. It gives you about 10 meters of accuracy. And the fine localization here locates you inside those clusters. One problem is anonymity. How can I be anonymous in this system where part of data is sitting in the server and I have to fetch that data and use it locally? So one way of solving this is this way. So you have your user, you have your service, which is sitting there. This is your database. And you have an authentication server that finds you as an eligible person to use that service. So what you do is you authenticate yourself with the server without exposing your location. You just say that I want to use the service. Okay? And you provide an ephemeral ID for this transaction. And this is not you, this is just something that you select on the spot. You're authenticated. These two guys, they talk. The authentication goes there with that ephemeral address. So basically, this guy doesn't know you. It just knows that ephemeral address. But it knows that this is authenticated. And then it starts giving you the service. So it knows that someone with this fictitious ID is using it, but it's authenticated. So this way, you don't really expose your identity to the service provider. So you're basically talking into having a three-way solution. When you're doing navigation, in this system, we are using the tracking. And this tracking is Kalman filter, as some of my colleagues today talked about, and seems to be a very promising method for finding or for correlating the data that you're collecting at different time instants. So let's talk about the implementation. What we did is that we tested this device in 3 places. At the University of Toronto, at the 4th floor of an 8-story building. At the Canadian National Institute for Blind, this is for blind people. And we went also to a shopping mall. This shopping mall has about 110 stores and about 400 square feet. And we use Windows as well as Android devices. Okay. This is the accuracy that you can get with this localization. Here you find the number of access points that you are using. The number of access points that you could see in your environment is, most of the places, public places, are about more than 10. But basically you need just 5 or 6 access points to be able to do the location. Now, if you are not clustering, this is the accuracy that you get, up to 10 meters or 20 meters. But if you're clustering, you get to sub 10 meters, which is about 2 or 3 meters of accuracy. Again, another test with using that, the previous one was not using the Kalman filter. Here you're using Kalman filter. As you can see, with the tracking, you can also reduce the, you increase the precision or reduce the error, and you go to below 2 meters, maybe to 1.5. Now the question is that what is that 1.5? What does it mean? Is what percentage of the time you get it? So I have here the cumulative distribution function, here CDF, which say if you're looking to 90% percentile, you get to about 3 meters. So the average here is about 1.5 meter that you're getting. But the good thing here is that in the worst case, basically 99% or almost 100% of the time, you're below 6 meters. So this is a testing place that we did. 3 routes here. We start here and go, turn left and right. And there is another one starting here, coming down to elevator, and another one going to find a fountain. We did this, we designed the system, and we gave it to 30 people which were blind. Okay? So we have these 30 subjects. They volunteered to test this device. We split them into 2 groups. These are testing groups and the control groups, 15 each. And we tested these 3 routes. And these are the specification of those routes, the number of turns, and the distances, etc. And this is the test results. So the left-hand side, these are the people who use this device to navigate. On the right-hand side, this is the control group. These people, they were given instructions, verbal instructions, by one of my postdocs. Okay? So as you can see, this is the blue one, is the one that's success, and this is failure. You can see that it's a big gap or margin between the two cases. While they're using this device, they can find, and in more than 80% of the time, the target or the place of interest. This is the same result for the second test, and this is the same result for the last test. I guess this is, the colors are mixed here. This should be, testing group is 100% blue. I don't know why it's red. Anyways. Roughly, or in average, 90% of the time you are successful versus about 60%. 60% of the time if you are not using this navigator. If you are given verbal instruction, you're able to find the location in 60% of the time, but not most of the time. We also went to a shopping center. So we didn't have the map. What we did is that this is the information kiosk at the entrance of the mall. You just take a snapshot of that, and then it just goes into the software. You work with that. Now, our definition, of course, and the accuracy is with respect to that map, which is on the entrance of the mall. But in this shopping mall, we could get to the 2 meter 2 to 3 meters of accuracy depending on where you are. So in conclusion, we have designed a system for blind people. It uses 2 steps, and I want to emphasize that this is important to do it in 2 steps. You have to do first coarse localization and then fine localization. A major challenge that you have to attack is outliers, removing the outliers, and this coarse localization does this job very well for you using this clustering. And this can also be used for object finding. One of those traces or tracks actually was to a fountain, small fountain, which was inside the wall. And of course, blind people, they couldn't find it, but with that instruction that was given by the device, they could do it. Okay? Everything is done on the mobile set, so basically privacy is satisfied. And that includes my talk.